Hi, team. We are ready for section 7.1, verifying trigonometric identities. Now, everything that is in the gray box we've already covered before, but we want to kind of review each of these. We have the reciprocal identities. So for cotangent of theta, remember that is the reciprocal of tangent theta. Secant theta is the reciprocal of cosine theta. And cosecant theta is the reciprocal of sine theta. We also have quotient identities. Those are the tangent and cotangent. Tangent is the quotient of sine theta over cosine theta. And cotangent theta is the quotient of cosine theta over sine theta. We also have the Pythagorean identities, the granddaddy of them all. Sine squared theta plus cosine squared theta equals 1. If you were to divide all of that by cosine squared theta, we would get tangent squared theta plus 1 equals secant squared theta. And if we took the granddaddy and divided it by sine squared theta, we would get the last one, 1 plus cotangent squared theta equals cosecant squared theta. And then we have the even and odd identities. Sine of the opposite angle will give the opposite sine value of theta. Cosecant being its reciprocal falls along the same rules. So cosecant of, we'll just say negative theta equals negative cosecant theta. Let's jump to tangent because tangent and cosine have the same rules. Both of those are odd, so we get for tangent negative theta, a negative tangent of theta. And same thing for cotangent. Cotangent of negative theta equals a negative cotangent of theta. Cosine and its reciprocal are the only even functions of the trig functions. So cosine of negative theta is exactly the same as cosine of theta. Secant of negative theta is the same as secant of theta. Now, a lot of these identities, these are the basic ones. They all have alternative forms. For example, we can write tangent as the reciprocal of cotangent. We can write cosine as the reciprocal of the secant, and sine as the reciprocal of the cosecant. So it really depends on what we're given as to what is helpful. Alternatives to Pythagorean identities, you could take any of those identities and solve for any of the parts that you want. So sine squared theta is the same as 1 minus cosine squared theta. Cosine squared theta is 1 minus sine squared theta. Tangent squared theta is secant squared theta minus 1. Or if you solved for 1, we would get secant squared theta minus tangent squared theta. And for the last one, if you solved for 1, we would get cosecant squared theta minus cotangent squared theta. Or if you solved for cotangent, cosecant squared theta minus 1. I know, very exciting. And again, it's not that you have to have all of these memorized, but it's nice to recognize, wait, I've got a squared trig function and I have a 1 that could be one of my Pythagorean theorem, alternatives where I can substitute and make my problem easier. And so you can do a little manipulation to see if you do in fact have one of those. So let's actually work with some of these. The only thing that we are given is the fact that cosine theta equals 5/8, okay? And we can remember that cosine of theta equals x over r. And we know that theta is in quadrant 4. So he's down here. We want to find the exact value of each of these functions using our trigonometric identities. Well, for cosine theta equaling 5/8, we can use the granddaddy in order to find our sine theta. So we can do sine squared theta plus our cosine squared theta. So that would be 5/8 squared equals 1. So sine squared theta plus 25/64 equals 1. So sine squared theta equals 1 minus 25/64. So 64 minus 25 gives us 39. So we get a 39/64. And so when we take the square root of that, we have the square root of 39. The square root of 64 is 8, but we're in quadrant 4. So in quadrant 4, we know that the sign values, which has the y in there, is going to be negative. So we get a negative square root of 39 divided by 8. So when you're taking square roots, or if you're working with any of these identities, be sure that you're using the correct sign for the quadrant that we're in. Now, tangent theta equals sine over cosine. So we want to put our sine value of negative square root of 39 over 8 and divide it by 5/8. The 8s will reduce. So for our tangent, we get a negative square root of 39 over 5. For secant theta, remember secant of negative theta is the same thing as secant of theta because it's the reciprocal of cosine. So if it's the reciprocal of cosine and the signs don't change, we just have an 8/5. No work to do. Now in example 3, they're wanting us to write tangent theta in terms of cosine theta, and you might want to put the word only. Well, we know tangent theta, again, is sine theta over cosine theta. So we need to use one of our identities where we can rewrite sine theta just in terms of cosine theta. Well, the one that comes to mind for me is the Pythagorean. So over here on the right, sine squared theta plus cosine squared theta equals 1. Sine squared theta equals 1 minus cosine squared theta. And then take the square root of both sides. And we get either plus or minus the square root of 1 minus cosine squared theta. So we can write tangent theta as plus or minus the square root of 1 minus cosine squared theta over cosine theta. We can leave it like that. In part B, they're wanting us to write that expression, 1 plus tangent squared theta quantity divided by 1 minus secant squared theta, in terms of just sine and cosine theta, and then simplify the expression so no quotients appear in the final answer, okay? So no fractions whatsoever. All right, so following the instructions, they just want us to rewrite in terms of sine theta and cosine theta. I noticed at the bottom we have 1 minus secant squared theta. We could factor out a -1 and make it a secant squared theta minus 1, and then do some substitutions, but we will go ahead and follow the instructions and write everything in terms of sine and cosines and simplify. So this will give us 1 plus sine squared theta over cosine squared theta for the tangent, divided by 1 minus 1 over cosine squared theta for my secant squared theta. Now, to get rid of the complex fractions, let's multiply top and bottom by that common denominator of cosine squared theta. When we distribute, we get cosine squared theta plus sine squared theta. And the denominator, we get cosine squared theta minus 1. The top is the granddaddy, which is nice, which is 1. On this bottom one, we could factor out a -1 and make it 1 minus cosine squared theta. And so we would recognize that as part of the Pythagorean, which would give us a negative sine squared theta. And that's the reciprocal of cosecant squared theta. So we simplified it so there's no quotients that appear in the final answer. So if you're wondering where this comes from, again, we've got cosine squared theta plus sine squared theta equals 1. That's the granddaddy. Remember what I said, whenever you see a squared trig function and a 1, you want to look to see, is this something that can be simplified? So if I solved for my sine squared theta, we would get 1 minus cosine squared theta, which is why we chose to factor out that -1 to put it in that format. So here are just some hints for when we're trying to verify trigonometric identities. We're trying to rewrite them to make sure that they're equivalent. because sometimes that makes solving problems later on a little bit easier using these identities. So some of the hints is when you're verifying identities, we're trying to prove that they're equal. So we can't work across the equal sign assuming that it's equal, okay? So we can work on the left side by itself, we can work on the right side by itself, but we have to work it separately. In other words, there's no adding something to both sides. We also try to generally start with a more complicated side, and then we can, try to break it down to make it look more like the simpler side. We want to look for any fundamental identities we can use to substitute or rewrite part of the expression to simplify it. Worst case scenario, rewrite everything in terms of sine and cosine, see what you could combine and rewrite. See if you can factor. Sometimes it's hard for people to recognize a quadratic when we're dealing with trigonometric functions, but it is in quadratic form, so maybe we can factor it. And then last, can we multiply like the numerator and the denominator by a conjugate to get some fundamental identity or to get something to reduce? So let's do some examples of verifying identities. We want to verify that this equation below is an identity. So this equal sign is really more of a question mark right now. The left side seems to be a little bit more complicated, so I'm going to start on that side. We can distribute the secant, but since inside the parentheses is sine and cosine, I'm going to go ahead and change that secant to 1 over cosine theta. Now we can distribute, and we get sine theta over cosine theta plus cosine theta over cosine theta. And that reduces to tangent theta plus 1, which is equal to the 1 plus tangent theta that we started with. Okay, so notice I only worked on one side. I didn't divide both sides by secant theta or anything like that. You're trying to verify that they're true. Now, on part B, it might seem as though we would rather work on the right-hand side first, and we can even start there. We would get 1 minus cosine t plus cosine t minus cosine squared t, which leaves us 1 minus cosine squared t. But it looks like there's going to be a lot of weird manipulation to try to go from there to the left-hand side. So it's okay if you start on one side and you're like, I don't see where that's going to take me, and then turn around and start on the other side. That's fine, as long as you work them both separately. So if we're working on the left-hand side, we've got the tangent squared of t divided by secant t. So we can write this as tangent squared t times the reciprocal, or 1 over secant squared t. Well, remember, secant is the reciprocal of cosine. So this is tangent squared t times cosine squared t. Tangent squared t is a ratio of sine squared t over cosine squared t. So this just gives us sine squared t. Well, the right-hand side is in terms of cosine. We can use the Pythagorean to rewrite this sine squared t as 1 minus cosine squared t. And that is factorable. It's a difference of two squares. So that will give us 1 plus cosine t times 1 minus cosine t. And that is, in fact, what we had on the right-hand side. Now, this last one, I wanted to show you an example of it because it can be a little disconcerting because there's so much going on. One thing that you may notice, though, is that the numerator on the left and the denominator on the right, those are conjugates. So what we may want to do is multiply one of those sides, top and bottom, by the conjugate and kind of see how things fall out. So let's just do it with the left. So we took the left-hand side and multiplied the top and bottom by secant x minus tangent x. When we distribute on the top, since they're conjugates, we get secant squared x minus tangent squared x over the bottom, which is sine x times secant x minus tangent x. Now, you may on the bottom be tempted to distribute the sine x or change the secant and tangent into sine and cosine. But remember what we want our function to look like. We want that secant x minus tangent x to be in the denominator because that's what we're verifying. So instead, let's leave those two factored on the bottom and deal with the top. Notice we have a secant squared x minus tangent squared x. That is part of the Pythagorean. That equals 1. Put yourself a note, Pythagorean identity. So we get 1 over the sine x times secant x minus tangent x. And again, we have the secant x minus tangent x in the bottom like we want. The only thing that's different here is we want a cosecant x in the top. But look what we have left. We have 1 over sine x. Remember, sine and cosecant are reciprocals. So this is the same thing as saying cosecant x divided by secant x minus tangent x, which is in fact our right-hand side. So always keep an eye on your goal, what you're trying to get it to look like, and that might save you some steps. I don't know every step on these verifications and how it's going to fall out. So don't put that pressure on yourself that you need to know what every step is going to look like before you try it. Try it like I did on that other problem. I worked on the right-hand side and it got me nowhere. So I switched and I worked on the left-hand side. Same thing for you guys, but just take your hints from the side that you're trying to mimic, the side that you're trying to get it to look like. Okay? So good luck with you guys, and I'll see you soon. Bye.